going to be discuss module 5 of automata theory and computability, that is a variants of Turing machine and model of the linear bounded automata concepts. So going to be discussed in the subsequent slides. So the presentation milestones as follows. So we'll little about decidability and decidable languages we have discussed anyhow in the model 4. The little about that going to be discussed in the model 5 too. Undecidable languages, also halting problem of Turing machine. So halting problem, we have seen that Turing machine will accept the string of the given, so then it will terminate. So sometimes what will happen, it may not accept the string and it will not terminate, neither terminate nor accept, neither accept nor reject. It will be in the loop, it will be in the loop. So that unnecessary loop consumes the time, computational aspects. So that's why the halting problem will be creates that, right? Halting problem. So that how this halting problem going to be noticed, so that will going to be observed in the subsequent discussion. So at the outset, the since the title will be invariants of Turing machine and linear bound automata, to in order to the establish the link for this subject, for this concepts, just we see that the linear bound automata, the set of sensitive languages is accepted by the model. The infinite storage is restricted in the size, right? So we have seen that linear bound automata, some restrictions are barcode putting to size, so otherwise it become Turing machine. So if you put some barcode or restrictions, then it become linear bound automata, but not in the accessibility of the storage in comparison with the Turing machine model. It is called that linear bound automation due to the linear function involved here. Linear function involved to decide the size of the memory is used to restrict the bound the length of the tape. So the in the Turing machine, that length is almost infinite. So here make it a finite. So then we can accommodate the that linear function, that is. So model of linear bound automata, so developed relation between the LBA and context sensitive languages. It should be noted that the study of sensitive language is important from the practical point of view, because many compiler languages lie between this sensitive and free languages, sensitive, context sensitive and context free languages. So in order to cater the needs of that compiler languages, so this is most important. So linear bound automata is a non-deterministic Turing machine which has a single tape and length is a not infinite, that is finite, but bounded by the linear function. So decidable, the definition of the recursive enumerable sets going to be say about decidable of these languages, recursive sets, enumerable and recursive sets. So notion that notation recursively enumerable set and recursive set exist before the computer era. Computer came to light, so before that also it was there in for classical languages. Now these terms are also defined using Turing machine. When Turing machine arrive at the final state, it halts. When it reaches the final state, it halts, right? So we can also say that the Turing machine model halts when machine reaches the state Q. So particular state Q in the machine, it reaches and halts and consumes the current input symbol to scan, that is a delta Q comma A is a undefined. So delta Q is a current state and current A is a current input. So delta is a transition. So delta Q comma A is equal to that is next Q state should be reached. So that is missing here. That is undefined. That is not properly able to decide. So that's why that halting problem may be occur. So there are Turing machine that never halts on some inputs. Some Turing machines are there. It will not halt never, that is. So it will keep wait for that certain inputs, or it will be hang. It will be in the loop. So they are in the loop. So in that loop, it is a cost of the computation aspects need to be assessed here, addressed here. So certain inputs or any of this way, so halt that is. So we make a distinction between the languages accepted by the Turing machine. That is halt on a all input stage. For all input string, the machine going to be halt. So that is language accepted. And Turing machine that never halts on a some input string. All inputs will be accept. So that is a language, and some inputs will not accept. So that is also language. So between these language, so there is a discrimination will be there, right? So that discrimination going to be decide. So that is the decidable. For defining recursive sets, we need the definition of the procedure and algorithm. For defining a recursive sets, so the procedure and algorithm is essential. So procedure for solving a problem is a finite sequence. Procedure for solving a problem is a finite sequence of instruction which can be mechanically carried out at a given input, given any input, right? So that procedure and algorithm is a essential for the recursive set this definition. So that procedure solving a problem is it happen in the now countable sequences of instructions which can vectorially or mechanically carried out given any input. An algorithm is a procedure which stops after countable number of steps, right? So that is a one the qualification that algorithm should have. What qualification? It should stop after a finite number of steps for any input, right? So we know the algorithm characteristics. A set X is a recursive. X is a recursive. If we have an algorithm to determine whether the given element belongs to X or not, so there is a array that is a recursive in nature. We want to find the element which is belong to that array X or not. So that is a noticeable observation here. Recursively, enumerable set is a set X for which we have algorithm to determine whether the given element exists or not, right? Recursively enumerable set is X for which we want to find an element which is a exist or not in that enumerable set. So that is a more elaborate way compared to the previous statement. So it is clear recursive set is a recursively enumerable. So here recursive languages are required to understand that. So we have a language L over the alphabet sigma. Language L over the alphabet sigma is called recursive, right? Recursive. If there is a Turing machine model able to consider every word in our L, every word in a L that was considerable or should be accepted, and rejects every word in a L dash, that is except M is equal to L. So reject M is equal to L cap, loop of M is equal to null. So that is a reject, accept is L, reject is L complement, accept F of M is equal to L, reject of M is equal to L complement, that is the loop of M. So empty. So example B, open bracket A plus B close bracket star, right? So that is a recursive language going to be accept or reject. Recursively enumerable language, a language L over the alphabet sigma is called recursively enumerable language if there is a Turing machine model that accepts every word in L. If every word of the language L is accepted by the Turing machine model, then we can call it as recursively enumerable language. And either the rejects or loops every word in a L cap, that is a what is called complement, L complement. Either rejects or loops, it will reject the string or hang in the loop, that is L cap. The complement of L accept, that is a M of, accept M of is equal to L, reject M of L, reject M plus loop of M is equal to L cap, accept M it is equal to language L. So reject M plus loop of M is equal to L cap. So that L cap is equal to reject M and loop of M. So both are together, both are added there, right? So that will be a the recursively enumerable language either should accept M for the language L or reject M for L cap plus loop of M. That is a example is equal to open bracket A plus B whole star close bracket, and B open bracket A plus B close bracket star. So that is an example for this consider, that is a what is that accept M for is equal to L or reject M plus loop of M is equal to L cap, that is a what we call complement of that. Okay, so let we see the problem, one problem. So that the enumerable DFPA, the deterministic finite automata, is equal to M, where M is a deterministic finite automata, and Turing machine is equal to MT is a decidable. So that enumerable deterministic finite automata is a M, right? What is M? M is a deterministic finite automata, a finite automata, deterministic finite automata, and Turing machine M is equal to MT is a decidable. So construct a Turing machine model as follows. Construct a Turing machine model as follows. After constructing, the A is an input to M. So A is an input to M. Mark the initial state of A, that is Q0. Mark the initial state Q0 and Q0 star a new symbol, right? For Q0 star A is a new symbol. So repeat until new states are marked up to new states, right? Marking is proceeding. A new states is marked if there is a transition from state already marked to the new state. So if there is a transition from state already marked to the new state, so we need to be consider the state transition from marked to new state. So if final state is marked, M accepts A, otherwise it rejects. So final state, that is also accept. If it is accept, that is A, or else it rejects, right? So final state going to be marking, necessity of the marking is only accept, otherwise it is reject. So that is a proof, that is. So second problem, so that the acceptable, that non-deterministic finite automata is equal to flower bracket, round bracket, b comma w. So that is b is a non-deterministic finite automata. N is a non-deterministic finite automata, and b accepts the w is a decidable. B accepts the string w. So b comma w is b is a current state, and w is a string. W is a string. W string. So where b is a non-deterministic finite automata, and b accept the w, so that is decidable. So this we want to elaborate further. The solution, first step, b comma w is an input to m. B is a current state, w is a string. W is a string of certain length, is going to be input to the machine model M. So that is clear. Convert B to an equivalent DFA. B will going to be converted to deterministic finite automata, right? So initially that is a non-deterministic finite automata. B is initially it is a non-deterministic. So now we need to convert into DFA. So run the Turing machine model M1, right? Turing machine model M1 for a acceptable deterministic finite automata on an input A comma W. On an input A comma W. So A is a deterministic finite automata on an input A comma W, right? So the conversion going on. If M1 accepts, M1 is what? Turing machine model M1, right? We will accept. So M accept, otherwise M rejects. So this Turing machine model M1 on behalf of deterministic finite automata, it will accept, then it will be accept, otherwise rejects. So that the equivalent, that is a deterministic finite automata, what we have A DFA is equal to A comma B, or A and B are a DFA. A and B are a DFA, and T of A is equal to T of B is a decidable. That is a T of A is equal to T of B is a decidable. So that is a Turing machine model M1, Turing machine model A, Turing machine model B. So is equal to decidable. If L is equal to T of A1 minus T of A2. So L is equal to T of A1 minus T of A2 union of T of A2 minus T of A1, converse. T of A1 minus T A2 union of T of A2 minus T of A1. So that is a L going to be considered. So L is a regular, and L is a equal to T of A cap, that is a complement. We have A cap, A1, A2. So apply that is a enumerable DFA to A cap, enumerable DFA to A cap. So the problem or language is undecidable if it is not decidable. So we know that problem language is not undecidable and it is not decidable. Language is decidable and it decidable. So language or problem is a solvable and it is a solvable. Unsolvable, it is a unsolvable, right? So solvable is a decidable. Unsolvable is a undecidable. Similarly, the problem or language is a undecidable if it is not decidable. So note, so decidable problem is called a solvable problem. Decidable is a solvable problem, and the undecidable problem is an unsolvable problem by some authors. some authors saying that so that is undecidable or unsolvable, solvable or decidable. So understood this, there is a reducibility. So language A Turing reducibly to language B to reducible when A is less than Turing reducible B, that is a Turing reducible B. A is less than Turing reducible B if A is a decidable relative to B. If A is a decidable relative to B. So it is shown that enumerable Turing machine is a Turing reducible to equivalent Turing machine. So enumerable is a Turing reducible to equivalent Turing machine. So whenever A is mapping reducible to B, A map to A reducible to B maps, then A is a Turing reducible to B, right? A is mapping to reducible B. A is mapping to reducible B, then A is a Turing reducible to B, right? Converse, that is. So the function in the mapping reducibility could be replaced by an oracle, that is. So the oracle Turing machine with an oracle for EQTM, equivalent TM, that is a can be decided enumerable TM, that is a enumerable TM. So oracle for EQTM can decidable E of TM. So enumerable TM is a Turing reducible to EQM, that is a equivalent Turing machine. So that Turing machine of EQ minus TM, that is a EQ minus TM on input 1, so create a model M1, create a Turing machine model M1, that is nothing but L of M1 is equal to MT. So MT Turing machine model will create. So M1 accept the transition from start to reject state for every element. It will be perform transitions. Call the EQTM oracle on input. Call this one, and it accepts, it rejects and reject it. So that EQM TM will be, EQM oracle will be accept, otherwise rejects. TQ of minus TN, TQ minus superscript T superscript EQ minus TM decidable E TM subscript, that is a equivalent enumerable Turing machine. So enumerable Turing machine is decidable relative to EQTM, is a decidable relative to EQTM. So the applications are, if A is less than the T of V, that is a T of V, and B is a decidable, then A is a decidable. So A is less than T of B, B is a decidable, and A is also decidable. A of less than TB, that is a and A is a undecidable, and B is also undecidable. So if A of less than or equal to TB, that is B is a Turing recognizable, then A is a also Turing recognizable, right? So these are the applications going to be derived from this theorem. So continuation of this can have that A of what is that A of less than TB, A is a non-Turing recognizable, then B is also non-Turing recognizable. Those are the applications. So decidable and undecidable languages, problem is said to be decidable if it is a language is a recursive, it has a solution. So example, decidable, does finite state machine accept regular language? Is the power of non-definite finite automata and DFA same? Undecidable. For a given context-free grammar, is a L of G is ambiguous, right? So decidable if it is a language is recursive or it has a solution. So example, decidable, does a finite state machine accept the regular language, and is the power of non-deterministic finite automata and deterministic? Say undecidable. For a given CFG is a L of G ambiguous. So L is a Turing decidable or just decidable. If there is exists a Turing machine model M that accepts all the strings in L, Turing machine model M, then it will accept all and rejects all strings not in L. Complement. Accept the all, rejects which is not in L. So note that by rejection means the machine halts. Rejection means machine halts after a finite number of steps, countable number of steps, and declare that the input string is not acceptable. So after consuming the finite number of steps, it declares that input string is not acceptable. There are two types of Turing machines based on this halting. The recursive Turing machine that always halts, no matter accepting or non-accepting. It is clearly declare the termination. It halts, it stops, right? So that is a recursive. So recursively enumerable Turing machine that are guaranteed to halt only on acceptance. Enumerable Turing machine that are guaranteed to halt only on acceptance. Only on acceptance. So if non-accepting, it may or may not halt. So it may not halt, no guarantee. Could be loop in forever. So that is a recursively enumerable Turing machine. So one that is halts, it have a clarity to terminate, it have a clear cut stopping criteria, so that will be recursive Turing machine. So recursively enumerable Turing machine, that is it no guarantee to halt, it acceptance. If non-accepting, it may or may not halt, that could be loop infinitely. So undecidable problems are those that are not recursive languages, right? Undecidable languages are not recursive. So decidables, undecidable problems are those that are not recursive languages, right? So that are not recursive languages. So halting problem, we can observe. The reduction techniques is exercise to show that undecipherability of the halting problem of Turing machine. So there are several techniques may be possible. One such class of technique called reduction technique is imposed to show the undecipherability of the halting problem. We say that problem A is reducible to problem B if a solution to problem B can be used to solve the problem A. So problem A transferred into problem B, right? Then solution for the problem exists. So that solutions we can employ over the problem A, right? So problem A and B, A have a solution, A do not have a solution, B might have, if and only if A reducible to B, right? A reducible to B, then solution is available for B. So that solutions we can employ or declare for the A also. So example, if A is the problem of finding some root x power 4 minus 3x square plus 2 is equal to 0 is a equation, right? Fourth order equation is there. So we need to find the roots. And B is the problem of finding some roots x square minus 2 is equal to 0. So A is the this fourth order equation. So B is a solution. B is a roots of this A, that is x square minus 2 is equal to 0. Then A is reducible to B. We can say A is reducible to B, right? So finding a problem for A is a difficult, but you can transform A into B. So B have some solution. So that solution is we can use for the problem of A. So that is the same thing happen here, right? So the reducible to B. So as x square minus 2 is equal to 0, as x square minus 2, x square minus uh, 2 is equal to 0 is a factor of x power 4 minus 3x square plus 2. A root of x square minus 2 is equal to 0 is also root of x square 4 minus 3x square plus 2 is equal to 0, right? X square minus 2 is a factor of this, and x square minus 2 is also root of x power 4 minus 3x square plus 2 is equal to 0. So that is a what we can say the halting problem clarity. The problem is reducible to problem B, and the solution to problem B can be used to solve a problem B. So that is a reduction technique to prove the undecidability of the problem, halting problem. If note if A is reducible to B, B is reducible, then A is a decidable. A reducible to B, B is a decidable, then A is a decidable. A is a pioneer. A is a leader here. If A is reducible to B, A is undecidable, then B is undecidable, right? A is reducible to B, then A is undecidable, then B is also undecidable. So the decidable A is a decidable, undecidable is also undecidable. So go to the crux of this halting theorem. So halting problem, that is halt the Turing machine is equal to m comma, that is a round flower brackets, round bracket open, m comma w, round bracket to close and flower bracket close, that is m is a machine and w is a string of Turing machine. Halts on input 1 1 is a undecidable. So for the input 1 1 is a undecidable. So proof, assume that halt T Turing machine is decidable and get contradiction. So we want to show that it is undecidable for the string 1 1. So assumption here decidable. This assumption maybe leads to contradiction. So let M1 be the Turing machine, that T of M1 is equal to halt T of Tm. So M1 be the Turing machine, that halt Tm of M is equal to halt Tm, and let M1 halts eventually on M comma W. So let M1 halts eventually on M comma W. We construct a Turing machine M2 as follows. We construct a Turing machine M2 as follows. So for M2, M comma W is an input. Earlier the M1 was there, M was there, now M2, the M comma W is input. The Turing machine M1 acts on M comma W. So Turing machine M1 acts on the input string W, which was for M2 also. If M1 rejects M comma W, M2 also rejects, right? So two parallel machines they consider, Turing machine the M1 and M2. For the both the input for the both the machines M comma W is a string. So if M1 rejects, then M2 also rejects. If M1 accepts, stimulates the Turing machine M on the input string W until M halts. So in the accept case, so simulate that Turing machine M on the input string W until halts, until M halts. So M has accepted W, M2 accept the W. M accepts, M2 accepts, otherwise M2 rejects, right? So the initial one is a M, later generated M1 M2, right? So M accepted, M2 also accept, otherwise M2 rejects. When M1 accept in step 4, that Turing machine halts on W. In this case, either an accepting state Q or q dash, accepting state q or q dash, such that delta of q comma a is undefined till some symbol in w is reached. That is undecidability is there. So delta of q comma k is a unknown in the sense the what is the next state, so delta of q comma a is a decidable, delta of q dash comma a, that is a accepting state. In the case q dash, q is a undefined, still some symbol in w is reached, so in the first case, the first alternative step 5, accept m comma w. First alternative step, it will m2 accept the m comma w. In the second case, alternative of step 5, m2 rejects m comma w, right? M2 rejects. From the definition m2, then m2 halts eventually. Also, Turing machine m2 is equal to m comma w, where the Turing machine accept w is equal to accept Turing machine. This is a contradiction since a of tm is undecidable. A of is undecidable. So that halts t of m2 is equal to m comma w. So the Turing machine accepts string w that is equal to a of tm. This is a contradiction. So it is a m halts m1 do not, m2 halts, so, or m2 halts, m2 accepts. In some case it will accept, some case it will not halts. So it will be remain in the infinite loop. So this contradiction, this dilemma, this oscillation will leads to the undecidability, right? Will leads to the undecidability for the string 1 1, right? So that is a halting theorem concept. So let me proceed. Algorithm for halting problem. So machine for halting problem. So input machine m and string w. So construct mw. Determine the if L of m is a infinite. If L of mw is a finite, determine if L of mw is a finite. Yes, then m does not halt on w. If determine the finite case, m does not halt on w. So no, then m halts on w. If it is not finite, then it halts on the w. So m halts on w. So if and only if that is L of m is not finite, L of mw is not finite. So during such case it only halts, right? So not finite. So we have, that is a discussion. There is a mw machine construct, it receive the w input, right? It's a construct, that is, so check L of mw is a finite, right? If so, then it will be halts, that is, otherwise no, right? Is a yes, no is a yes, right? So that from this can able to understand L of mw, that is the algorithm for halting, is a finite. It is yes case, then it will no, right? The machine yes, then machine does not halt on w. If no, then yes, machine halts on w, right? So that is a flip-flop kind of mechanism will be exercised in the halting theorem. So from this diagram we are able to clear it, the concept. Let m be the machine that accept the language L, that is L of m. So assume that we have two strings algorithm. So the algorithm for two string problem, that is a machine m, and that is it will accept the fm and contains two equal strings, then no, then does not contain, right? So does not contain. Two strings are equal, then it is a contains in S case, if no, and then does not contain. So, algorithm for halting problem, the is a yes, it is contains m halts on w, it does not halt on no. So the above one is a algorithm for twisting here halting problem. So yes will be m halts and no will be does not halt, that is. So continuation of this we have, that is a, so the difference between the that is a acceptable Turing machine and halt Turing machine. Difference between acceptable and halt Turing machine. So here the acceptable Turing machine is regarding Turing machine accepting an input, that is reaching an accepting state after scanning W, string W. After consuming or after reading complete the character which is available in a string W, then it's going to be accept, then reach in a accepting state, right? So it's going to be reach the final state. So that is happening, that is. So halt Turing machine accepting, that is a of Tm, that is accepting. Halt Tm is regarding a given Turing machine halting an input, halting on an input, or M need not accept W in this case. So strings may accept or not accept, need not accept. So regarding that Turing machine not accept, that is, right? So that is a halt Turing machine, halt Turing machine, right? So halting an input need not accept the W string. So that the set of all real numbers between 0 and 1 is uncountable. The uncountable between 0 and 1, a set is uncountable if S is a infinity. There is no one-to-one correspondence between S. Then the set of all natural numbers, right, between 0 and 1 we can real numbers we can find. So solution, represent a number between 0 and 1 as a 0, a1, a2, so on, that is till a1, a2, where a1, a2, a3 are binary digits, right? Binary digits 0, 0, 0, 0, 1, 1, 0, so on, that is where it's a binary digits. So assume that set to be sequence and apply diagonalization process. So sequence, apply diagonalization process and get a contradiction, right? Get a conflicts, that is. So why you should study one undecidable solution? So when the problem is undecidable, we can modify or take the particular case of the problem and try algorithm. So modify the take particular case and try for that. Studying undecidable problem may spark an imagination to get a better ideas on computation. So undecidable problems are challenging problems. For that it is quite avenues to generate the solution, produce a solution for the some complex problems. So that's why there is some ignition may be possible, imagination ignition may be possible to get a better solution. Prove that there is a recursive problem type 0 grammar is unsolvable. So unsolvable. So suppose there is a problem is solvable, then there is a algorithm decides whether the given terminal string W is in L. W is in L. So let M, machine M be the Turing machine. There is a grammar G such that L of G is the same as setup accepted by the M. Then W string is belongs to L of G if and only if M halts on W. String is a member of this language if halts on that. This means that the halting problem Turing machine solvable, which is contradiction. Hence the recursiveness of type 0 grammar is unsolvable, right? So the unsolvable, consider here some contradiction or conflicts. For certain time it will be halt or sometime it not halt. So this discrimination between halting and not halting is solvable, which is a contradiction. So hence the recursiveness of type 0 grammar is unsolvable. So with this we can see that the problem here, so that there is a exist Turing machine m over 0 comma 1 and state q of m is such that there is no algorithm to determine whether the or not m will enter into the state qm and begin with a given id instant in description. So there is no guarantee to reach to the state qm. Suppose there is exist in Turing machine m over 0 comma 1, that is a state qm, such that problem determine whether m will enter qm is unsolvable. So define Turing machine m cap, which is simulates the m complement, which simulates the m and has the additional transition provided delta of q comma a is a symbol is equal to qm comma 1 comma r, qm comma 1 comma r. Next, that is the input will changes and tape direction right side. Then m enters the qm when start with a given tape configuration. If and only if m cap, that is a m cap prints 1 when it starts with a given tape configuration, start with a given tape. Hence this given problem is unsolvable, right? So m dash prints then given tape is a configuration, then hence the given problem is unsolvable, right? So here we have the further discussion about this concept, that is we referred the following books to discuss the concept of this decidable, undecidable, halting and some of the problem form. Ilan-Rich automatic computability complexity edition, that first edition Pearson Education, and Mishra and Chandrasekharan third edition Theory of Computation Science. From this we derived the most of the material for this model 5, and other reference books too, Hopcroft et al., that is Introduction to Automata Theory Languages Computation, Pearson Education. Michael Sipser is an Introduction to the Theory of Computation third edition, Cengage Learning 2013. John Martin, Introduction to Language and Theory of Computation third edition, Tara McGraw Publishing Limited. So thank you for patient listening the topic decidability and decidable languages, undecidable languages, and halting problem of Turing machine. Thanks for coordinator, moderator and subject expert. Thank you one and all.